Welcome to this presentation on From Bits to Qubits, Superposition and Quantum Parallelism, presented by Professor Gottapu Sasibhushana. We will start with the difference between a classical bit and a qubit, and then examine the representation of single, two, and three qubits using basis states, superposition equations, and state vectors. We will see how the number of quantum basis state amplitudes increases from 2 for 1 qubit, to 4 for 2 qubits, 8 for 3 qubits, and in general 2 for n qubits, the key idea behind quantum parallelism. This slide shows how quantum computational power grows from bits to qubits. A classical bit has one definite state at a time, either 0 or 1. One qubit has two basis state amplitudes. 2 qubits have 4 amplitudes. 3 qubits have 8 amplitudes. In general, n qubits have 2 basis state amplitudes. So, the quantum state space grows exponentially with the number of qubits. This is the basic idea behind quantum parallelism. This slide explains the representation of a single qubit. A general qubit state is written as psi equals alpha kate 0 plus beta kate 1. Here, kate 0 and kate 1 are the computational basis states. Alpha and beta are complex probability amplitudes. The normalization condition is modulus alpha squared plus modulus beta squared equals 1. The upper right figure gives a simple picture of a qubit as a combination of the 0 and 1 states. The blotched slier below gives the geometric representation of the qubit. The point on the slier represents the state of the qubit, defined by the angles theta and phi. Thus, unlike a classical bit, a qubit can exist in a superposition of 0 and 1. This slide explains the representation of 2 qubits. 2 qubits have 4 computational basis states, kate 00, kate 01, kate 10, and kate 11. A general 2-qubit state is a superposition of these 4 basis states. It is written as psi equals alpha 00 kate 00, plus alpha 01 kate 01, plus alpha 10 kate 10, plus alpha 11 kate 11. The 4 alpha terms are the complex probability amplitudes corresponding to the 4 basis states. In column vector form, these 4 amplitudes are written as a 4-element state vector. The sum of the squared magnitudes of these amplitudes is equal to. This slide explains the representation of 3 qubits. 3 qubits have 8 computational basis states, from kate 000 up to kate 111. A general 3-qubit state is a superposition of all 8 basis states. It is written as psi equals alpha 000 kate 000, plus the remaining 7 basis states with their corresponding amplitudes. In column vector form, the state is represented by 8 complex amplitudes. The normalization condition states that the sum of the squared magnitudes of all 8 amplitudes is equal to 1. So, with 3 qubits, the quantum state space contains 8 basis states. This slide shows the main difference between classical bits and quantum qubits. On the left side, we see 3 classical bits. Each bit can be either 0 or 1. So, 3 classical bits can form 8 possible combinations. But at any moment, a classical system can hold only one combination at a time. In this example, the state is 101. On the right side, we see 3 quantum qubits. A qubit is different from a classical bit. It can exist in a superposition of 0 and 1. So, 3 qubits can represent a combination of all 8 basis states together. The equation shown here tells us that the quantum state is a combination of vertical bar 000, vertical bar 001, vertical bar 010, vertical bar 011, vertical bar 100, vertical bar 101, vertical bar 110, and vertical bar 111. This is the basic idea of quantum parallelism. A quantum computer works with many possible states together, while a classical computer works with only one state at a time. So, in simple words, classical bits, one state at a time. Quantum qubits, superposition of many states. That is why quantum computing is powerful.